voice and video clear to all? Tell me. So in today's class, we discuss about the problems on Taylor theorem. There are many problems on that, which I pick up those problems which are useful in the exam point of view. The underlying idea for all these problems is nothing but using the three Taylor theorem statements or some of the theorem statements. We are going to prove the required result as per the problem asked. The general approach is we go with a contradictory way in general while proving many of the problems. We need to make use of the three statements or one or two statements as per the need of the problem. The outline is nothing but whenever the order of a group is given to you, we are just determining how many normal subgroups will be there, or if there is no normal subgroup, then it will become a simple group like that. This is the general part of the question asked in exam point of view. So if you understand the logic of problem, similar kind of logic will be applied for the others too. Okay? So irrespective of the order of the group, if you understand the logic of one problem, the similar logic will be applied for the others too. Did you get that? Tell me. Now, let me take the first problem now. Just give me a moment, I will write the problem. So please take a note of the question, then I will discuss the cases one after the other. So after noting, you please inform. So is my voice audible to everyone? Tell me. Right. After noting, you please inform. I think everyone has studied the statements of silo theorems. Am I correct? Because that is essential in understanding the today's session. That's why I have given yesterday the statements of those theorems. Now see, this is a finite group which is having 30 elements in it. The order of the group is 30. So immediately what we have to do, always we should consider the prime factorization for the group order. So if you consider the prime factorization, it is nothing but 2 into 3 into 5. Accepted? Whenever you got the prime factorization, observing the primes in it, so it will have a silo 2 subgroup, silo 3 subgroup, silo 5 subgroup, because 2, 3, 5 are the prime numbers available in the factorization of 30. Clear? Are you clear or not? Because taking confirmation every time from your side is important for me in explaining the logic. So we are not discussing about silo 2 group here, because in the question part it is not at all asked. However, even though a question is framed, understanding case 1 logic, you can easily prove that. So let us go with the case 1. In the problem, what he is saying or what we have to show, silo 3 subgroup or silo 5 subgroup is normal in G. It means that if there exists a subgroup, silo 3 subgroup, what does that mean? The order of the subgroup is 3 because the prime number is 3. Similarly, silo 5 subgroup means order of the subgroup is 5. In that, each element will possess the order 5, that is by default implied. So order of the subgroup is 5, order of the subgroup is 3. If you know how many such subgroups we will get, then those subgroups are normal subgroups of G that we have to show. Understand that among these two, 3 subgroup or 5 subgroup, only one is normal. Both cannot be normal. Silo 3 subgroup, silo 5 subgroup, both cannot be normal. Either the first one or the second one, only the normal subgroups of G. Is the question context clear to all? Now, we know that if you want to know how many number of subgroups existed with respect to a prime number, I have given a specific formula as per silo third theorem that 1 plus Kp, and this 1 plus Kp will divide order of the group. This indicates the number of subgroups we are getting. So, if you want to calculate 3 subgroup, silo 3 subgroup, it is nothing but 1 plus 3k. This must divide 30. So obviously, if you substitute k is equal to 0, 1 divides 30. Accepted? Yes or no? It means that 1 plus 3k indicates how many number of such subgroups will exist. If k is equal to 0 means there is exactly one subgroup. So there is exactly one silo 3 subgroup. Please understand. So that is one case. So by substituting what value in k, 30 will get divided. 3. So if you substitute k is equal to 3, then 1 plus 3k is nothing but 10. 10 divides 30. You accept it all? So what happens? The number of silo 3 subgroups are either only one subgroup or you will get 10 subgroups. Did you get the idea? Now, there is a small result that if there is exactly one subgroup, then by default it is normal. There is a small result that we don't discuss, but you remember that if the P subgroup what you are calculating exists exactly one, it is always normal. Okay? So the first case is a trivial one. If there exists exactly one silo 3 subgroup, it is normal. Now what happens? What is the possibility that 10 silo 3 subgroups will exist or not? Let us go and think about that. Okay? Are you getting the context what I am explaining? Yes or no? Right. So if there are 10 subgroups, what does it mean? Each subgroup will has order 3 because I am calculating 3 silo subgroups. So whatever the subgroup you consider, by default it contains identity element accepted. So each one will possess identity. If a subgroup will has 3 elements, excluding identity, it will possess 2 elements. Agree? If a subgroup contains identity element, excluding the subgroup, so you will have 2 elements because the total number of elements in the subgroup are nothing but 3. Yes or no? Are you getting any trouble in understanding the context? If you have a small doubt, I will write. Let me say, I have taken 10 subgroups, H1, H2, so on, H10. These are total 10 subgroups. By default, every subgroup will possess identity element. This contains identity, so on, this contains identity. Please understand, 3 subgroup means the total number of elements in this set are nothing but 3. Here also 3. Here also 3. Now what happens? If you remove the identity element in it, it contains 2 elements. Accepted? Exactly. The order of subgroup is P itself or some power of it as per the thing you have taken. Please understand, if I say P square has come, so you will get a subgroup of order P square, that is Silo first theorem. Please understand, if P power m divides, then order of the subgroup will be of the form P power m. Clear? So here it has only power 1, so we are considering only order 3 or order 5 or order 2 only. Did you get it now? Right. So, excluding identity element, in each subgroup you have 2 elements, total 20 elements. The very definition of P group means in that group, element also has order the power of 3. It has order 3, let me say, in particular. Since you are talking about 3 group, the remaining 2 elements in the first group are of order 3. Second group are of order 3. So on, last group are of order 3. So what happens? All the 20 elements are of order 3. Okay? And all these elements are distinct. Please understand. So what you got? We got 20 elements are of order 3. Right? Now, so this resolution I have considered by assuming that there is more than one silo 3 subgroup. If there is exactly one, it is normal, it is okay. If there is more than one, then how many subgroups we will possess? 10 subgroups we will get. So in the 10 subgroups, excluding identity elements, if you take the remaining elements, we will get 20 elements which are of order 3. That was the resolution made from me. Okay? Clear to all? Please specify. Now, if you consider silo 5 subgroups, again, we will apply the same formula. 1 plus 5k should divide the group order. So, if you take k is equal to 0, there will be exactly one silo 5 subgroup. So, if there is exactly one silo 5 subgroup, by known result, it is normal, it is okay. Now, what happens if there is more than one silo 5 subgroup? Then we should know how many such subgroups will exist. So, as we know, the number is 1 plus 5k. By taking what value in place of k, 30 gets divided. By taking what value in place of k, 30 gets divided. One, am I correct? 6 divides 30. So if k value is 1, this total value is nothing but 6. So we will get 6 silo 5 subgroups of order 5. 6 silo subgroups of order 5. Each subgroup is of order 5. Now see, that means first subgroup contains 5 elements, second subgroup 5 elements, third subgroup 5 elements, like that. Just like in the previous case, what we discussed, excluding the identity element, in each subgroup we will get 4 elements because the total elements in the subgroup are 5. If you remove identity, you will get 4 elements. So how many such subgroups are there? 6. So each subgroup contains 4 elements. Total we will have 24 elements. What is the property of these elements? Each element will has order 5 because we are talking about the P group. So each element has order 5. So total 24 elements will has order 5. Okay? Are you clear? Now see, in the first part of the question, it was asked that among the 2 P subgroups, 3 or 5, whatever you consider, either 3 subgroup will be normal or 5 subgroup will be normal. Both cannot be normal. That was the thing asked. Am I correct? That was the question part. Now see what happens if both are normal. So all the 3 subgroups are normal, all the 5 silo subgroups are normal. So just for discussion, Yeah, as we know, how many such subgroups will existed? See, if 3 silo subgroups existed, you got 20 elements. If 5 silo subgroups existed, you got 24 elements. So total will be 44 elements in the group, because if this is the group G, whatever the subgroups you consider, the elements are nothing but part of the whole group. So here I am saying that there are 20 elements, and I am also saying that there are 24 elements. So total 44 elements will be there in the whole set. But actually G contains the maximum number of elements is 30. So you cannot insert 44 elements in 30. So both 3 subgroup and 5 subgroup cannot be normal. Either the first one or the second one should be normal only. That was the proof of first part. Please understand. Are you getting that? Yes or no? Yeah, I will say. This is the part asked. Agree? Either 3 or 5 silo groups must be normal. Both cannot be normal, right? I am saying that if both are normal, then what happens? That is my thinking. The 3 subgroups, how many are existed? All are normal. The 5 subgroups, how many existed? All are normal. Let us think like that. So just now we discussed that if they existed, then you will get 20 elements of order 3 for 3 subgroups. In other words, you will get 20 elements of this type, and of this type you will get 24 elements. These are the elements in the subgroups. So 20 distinct elements of type 3, 24 distinct elements of type 5. Total you will get 44 elements. Actually, all the elements in subgroup by default belong to the group G. So the maximum capacity of G is nothing but 30. So how can you insert 44 elements in 30? Did you get it now? So it is not possible. It is a wrong thing. So the only possible thing is the subgroups of type 3 should be normal. These are not normal. Or type 3 are not normal. Only type 5 are normal. Clear? Both cannot be normal. If both are normal, we will get a contradiction because you are having 44 elements. That was the idea behind it. Is everyone getting the context? So for the first time, if you are learning problem on silo theorem, you will get much confused. If you understand the definition clearly, theorem statement clearly, then it is very easy to resolve the solution. The logic what I am saying here can be understood properly. Let me say. In a simple thing I will mention. If you calculate subgroups of G, you will get two things. Type 3 model, type 5 model. What is meant by type 3? A subgroup having 3 elements. What is meant by type 5? Subgroup having 5 elements. He is saying that since the subgroups are existing, you calculate all the type 3 model, you calculate all the type 5 model. He is saying that either this model will be normal or this model will be normal. Both cannot be normal. That he is saying in the problem. Okay? Does it make sense? Right. So I am saying that suppose type 3 all subgroups, type 5 all subgroups are normal, let us say. Then what happens? This type will contain 20 elements, 20 distinct elements. This type will contain 24 distinct elements. So total you will get 44 elements, 44 distinct elements in the sets. But the maximum capacity of G is 30. So you cannot insert 44 into 30. So both types becoming normal is not possible. So either this type or this type only should be normal. Okay? Am I correct? I mean, are you getting correctly the way I am expressing? Any other questions for anybody? Yeah. We will talk about the condition 3 later. Don't worry. Fine. Now can I go with the case 2? Fine. Now I am talking about the case 2. Now he is saying that G has a normal subgroup of order 15. G has a normal subgroup of order 15 that we need to prove. Now we know that G possesses type 3 model, type 5 model. So let us take H is type 3 subgroup, K is type 5 subgroup. Let us take that. Now what happens? As per the previous case discussed, among these two only one will be normal, either H or K. That is the only possibility. Now we know that whenever one subgroup is normal, if you consider the product, because normal subgroup commutes with every subgroup, so it is also a subgroup. So HK is also a subgroup. While doing subgroups, we have taken result that if you have a normal subgroup, if you multiply with this another subgroup, the product is a subgroup. I have given a result. So either H or K may be normal. It is not the case of conjugate, please understand. If one group is normal, if you multiply a normal subgroup with another subgroup, result is a subgroup. Okay? That you understand. The result is a subgroup. So HK is a subgroup here. Now, I want to calculate what is order of HK. I just want to know. Okay. So, as we know, order of H is equal to 3, order of K is equal to 5. So, we have a small result that order of H intersection K is nothing but 1 because these are relatively prime numbers. Because intersection divides H, intersection divides K, because intersection is a subgroup of both sets. So I want a number which is dividing 3 as well as 5. The only possibility is 1. So order of H intersection K is nothing but 1. Now the old result what we have done is, if you consider order of HK, it is nothing but order of H into order of K by order of H intersection K. This result we have done in the subgroups. So this is equal to 3 into 5 by 1 is equal to 15. Okay. So I got that HK is a subgroup of G with order 15. But as per the case 2, I have to show that this subgroup is a normal subgroup. That part is left over. It is very simple. Whenever you have a group and subgroup, we can calculate the index. So if you calculate G is to the subgroup HK, nothing but order of the group by order of the subgroup, it is nothing but 30 by 15, 2. In group theory, we did a small result that whenever index is 2, it is a normal subgroup. While dealing with the theorems of normal subgroups, we did that. Whenever index is 2, it is a normal subgroup. Therefore, HK having index 2, it is a normal subgroup. Therefore, the part 2 completes. Now see, unless we have command over subgroups, normal subgroups, Silo theorems, all other results, we cannot solve problems based on Silo theorems. That was the difficulty here. So whenever a question is asked, usually the weightage will be 15 or more than 15 marks. That was the problem. But once you mastered with all these results, then you love to solve similar kind of problems. But initially it is very difficult to understand the logic and apply the logic for other problems. Okay. The one way of thinking is, based on the question part asked, we are going to decompose the solution, how to do using Silo theorems. That's it. Are you clear now? So did you get the case 2 part? Everyone? Shall I take case 3? Tell me. Yeah. Now, case 3 is an interesting one. Actually, case 3 looks that Silo 3 subgroup, Silo 5 subgroup, normal in G. As one of our friends asked that, as per case 1, this is a contradiction. Actually, we need to understand that if both existed, then both will become normal. That is one way of thinking. Second thinking is, how many such groups will exist? The number of groups. With respect to case 3, I will say that there will be exactly one type 3 group, one type 5 group. More than one, it is not possible. So whenever there is exactly one group, it is normal. So type 3 becomes normal, type 5 becomes normal. Therefore, the third statement becomes correct. That was the underlined idea here. Okay. In case 1, type 5 may exist more than 1. Type 3 may exist more than 1. So that either of the things only normal. In case 3, we are saying that there is exactly one subgroup of type 3, one subgroup of type 5. Therefore, both will become normal. That is the underlined idea of type 3. Okay, the case 3 part. Did you get the logic now? Yeah. Now, so this is the hierarchy thing. Say the topmost group is 3, G having 30 elements. Just now we proved that HK (15), the group of order 15, and another thing is this is one hierarchy. So this is type 3 group, type 5 group. Let us take like that. So HK is the product group. This is the topmost group. Now I am debugging the possibilities. Let me say type 3 is only one group. Type 5 is more than one group. Let us say this is one possibility. Another possibility is type 3 more than one group. Type 5 only one group. The third possibility is type 3 one group, type 5 one group. I am using the word type because every time if I pronounce silo 3 subgroup, you will get confused. That's why I am using the word type 3, type 5. So this is the possibilities when you consider the subgroups. Among the 3 possibilities, I want to show that this possibility will be ruled out, this possibility will be ruled out, only this possibility will exist. Then this is exactly one subgroup, this is exactly one subgroup. So this is normal, the part 3 gets completed. That was the idea behind it. Okay. So type 5 more than 1 means 5 subgroups are existing more than 1. Type 3 more than 1 means silo 3 subgroups are existing more than 1. That was the idea while checking the possibilities. Okay. Are you clear? Let me know. So is everyone getting confused over this? Say. Are you feeling it is difficult to understand the idea behind the silo theorems? Can I continue then? Hello. So by taking input from your side, then I will continue. Please understand that if the silo third statement says that the total number of type subgroups are of the form 1 plus kp, it is a divisor of the group. So here I am saying that if you take a group of order 30, there will be exactly one, the other possibilities will be ruled out. So if you take type 3 model, the number of subgroups existed is nothing but either you should have exactly one or 10 subgroups of type 3. Here the possibility. Here there should be exactly one of type 5 or 6 subgroups of type 5. Either of the case is confirmed. Right? Now I am saying that more than one is not a correct thing for the cases that we want to discuss. Clear? Now let me go with this. Did you get the hierarchy? What I mentioned here? Tell me. The hierarchy, right? Now, at this point, there is a small result. After the completion of third case, I will discuss. The result says that whenever you have a group, the order is of the form PQ. P and Q are primes. Let me say 3 into 5, 3 into 7, like that. So whenever you have the group order is product of two distinct primes exactly, then that subgroup is cyclic. That subgroup is cyclic. There is a small result. So here we have the subgroup HK having 15 elements. So this is a cyclic group. Now we should know how many generators will be there for a cyclic group. We have a formula phi of n. So if you calculate phi of 15, it is nothing but 8. So this set contains 8 elements of order 15 because order of the cyclic group is equal to order of the generator. So the subgroup HK contains 8 elements. They are exclusively different elements. Okay. Now let me take this possibility. Why this becomes wrong? Let us think that. Now see, this is type 3. I am saying it is exactly one group. So this group contains 3 elements. So if you take the second possibility, type 5 should be 6 groups. Earlier we have discussed that excluding identity element, 6 4's 24 elements will be here. So what it means, H contains 3 elements. Type 5 model, you will get 24 elements. This contains 8 elements. Total 24 plus 3 plus 8, 31. Sorry, 27 plus 8, 35. So it is excluding the group order. So this possibility is wrong. I am calculating the number of elements. Please understand. I am saying type 3 is exactly one group. Type 5 is not one. There are 6 groups existed. Let us take. Then as per the discussion, this model you have 24 distinct elements. This model is having 3 elements. HK contains 8 elements. Total 35 elements will be there in the group. But G contains only 30. So this is not a possibility. Clear? Are you getting it or not? Suppose if you take this possibility, type 3 is having 10 subgroups, type 5 is only one subgroup. So this set contains 5 elements. Earlier, excluding identity, each will contain 2 elements. 10 2's 20 elements will be here. This is containing 8 elements. So 20 plus 8, 28. 28 plus 5, 33 elements should be there in the total group. But G is having only 30 elements. So this is also not a possibility. Therefore, this is the only one possibility. Type 3 is exactly one subgroup existed. Type 5 is exactly one subgroup existed. Therefore, since this is only one group, this is normal. This is only one group, this is normal. Okay? So in this way, we prove the three cases or three parts of the problem. So I have taken all the possible cases in one single problem so that you can execute that in incorporating the idea. So if you are clear, I want to take the other model. Can I? So with regard to silo theorem problems, I will say that you just go with the UPSC previous year exam papers. So whenever an example is similar to that, you just copy that example, mimic that proof so that you can solve the problem. Not more than that, you don't pay any attention towards solving similar kind of problems. It involves a lot of logic. It takes much time also in getting the desired proof. So that's why I have taken that this is the last part in the course structure. So with regard to abstract algebra class sessions, I am taking the problems and silo theorems at the end only. Why? Because once you deal with problems on this type, you will get more confused. That's why we are not dealing in the beginning. I hope you will understand after discussing with the first problem. Okay? So the problem is, this is the problem I am taking. Suppose order of G is equal to PQ. P comma Q are distinct primes. P is less than Q. And P does not divide Q minus 1. So we have to show that G is cyclic. Actually, based on this result, a problem is asked in UPSC that show that a group of order 15 is cyclic. So 15 is nothing but 3 into 5, which satisfies this criteria. PQ, P is less than Q, P does not divide Q minus 1. This thing is exactly satisfied for this result. So if the same question is given in the exam, we simply write the result of this thing, the proof of this result, and straight away we mention that a group of order 15 is cyclic. Straight away we mention like that. Otherwise, observing the steps of this proof, same proof we can apply here for 3 and 5. Okay? So this is a previous year question. Now let us discuss with this. Have you noted the question part? Right. Now see, in this problem we have to show that G is cyclic. So whenever P and Q are prime numbers, they are involved in the group order, definitely we will get silo P group, silo Q subgroup for G. Now the question is, how many such subgroups will exist? That was the question here. So if you talk about P subgroups of G, then what happens? They are of the form 1 plus Kp such that it must divide PQ. So the possibility is, since 1 plus Kp cannot divide P, so 1 plus Kp must divide Q. So the possibility is K is equal to 0 or 1 plus Kp is equal to Q, because Q is a prime number. Accepted? Please check on that. Please observe what I have written. So here I am talking about how many P subgroups will exist for the group G. As per third silo theorem, the number of such subgroups is of the form 1 plus Kp. So 1 plus Kp will give the number of subgroups of type P. This number should divide group order. So if you want to say that 1 plus Kp should divide this product, this value is not dividing P. So the only possibility is this value should divide Q, because this is the product of two primes. If you want to say that whenever the result is a product of two primes, one prime should be divided by this divisor, otherwise product will not get divisible. So 1 plus Kp should divide P, or 1 plus Kp should divide Q. First case is not possible because 1 plus Kp cannot divide P if K is a non-zero value. So 1 plus Kp must be equal to Q, because 1 plus Kp should divide Q means Q is a prime number. So 1 plus Kp must be equal to Q. Do you accept now? So it means that Kp is equal to Q minus 1. So if you multiply P with some number, you are getting Q minus 1. It means that P divides Q minus 1. But in the problem, it is given that P will not divide Q minus 1. So this is wrong. While saying that this is wrong, I mean that K is equal to 0 is the only possibility. If K is equal to 0, if you substitute, there will be exactly one silo P subgroup. This is the resolution. Okay? With regard to silo P subgroups of G. Any questions? Right. Now, if you calculate about Q subgroups of G, how many Q subgroups will exist? Right? Here also we apply the same thing. The number will be of the form 1 plus K into Q. It must divide the group order. So, as it is given that P is less than Q, so 1 plus KQ does not divide P. Sorry, 1 plus KQ does not divide Q, because this is the multiple. So 1 plus KQ should divide P, implies 1 plus KQ is equal to P, implies K into Q is equal to P minus 1. Therefore, what happens? Q must be less than or equal to P minus 1. Q must be less than or equal to P minus 1. As per the thing, consider it. So it means that Q less than or equal to P minus 1 and P minus 1 is less than P. This is a contradiction, because in the problem it is given that P is less than Q, strictly less than Q. So this thing is not correct. So it means that there is exactly one silo Q subgroup. There is exactly one silo Q subgroup, just like the previous case. You take a note of that, then inform me. Are you clear what I have resoluted there? Now, so we have calculated how many P-type subgroups will exist, how many Q-type subgroups will exist. So we confirmed that P type will be exactly one subgroup, Q type will be exactly one subgroup. Now, what does it mean? So, there is exactly one subgroup, say H, such that order of H is equal to P. P type means subgroup order is P. Similarly, there will be exactly one subgroup of type Q. That means order of the subgroup is Q. Here P is a prime number, Q is a prime number. Okay? Did you get that? So, in cyclic groups, we observed that a group of prime order is cyclic. A group of prime order is cyclic. Now, what happens? This is a cyclic group, this is a cyclic group. So let us take the generators. So please take a note of that. So we have two subgroups, both are cyclic, and those are their respective generators. And remember one more thing, whenever there is exactly one subgroup, they are normal. So this is a normal subgroup and this is also a normal subgroup. Are you clear? Now again, going back to normal subgroup properties, whenever you have two normal subgroups, if you say H intersection K, if this is only having identity element, if it is only having identity element, are you getting what I am saying? Yeah. So, if you consider order of Hk, this is nothing but order of H into order of K. So, this is nothing but, in other words, P into Q, the value. So, in a simplified manner, we can say like this. If you consider the order of the element AB, since order of A is equal to P, order of B is equal to Q, P comma Q are prime numbers, so GCD is 1, therefore order of AB is equal to order of A into order of B. This is the properties of order of the elements. So this is nothing but 3 into 5, 15. If you take the prime numbers as 3 and 5. If you take the prime numbers as P and Q, it is nothing but P into Q, PQ. So what happens? AB is an element whose order is PQ. It is equal to the group order. Whenever order of the group, order of the element are equal, so this is nothing but the generator. So I have calculated a generator for the group. Therefore, the group G is cyclic. That was the conclusion. So if you look at the whole synopsis, we have simply done 3 steps. The whole synopsis is nothing but 3 steps. Step 1, using Silo theorems, I have taken 1 plus Kp, 1 plus Kq, and I resoluted that there is exactly one subgroup of type P and type Q. In the second step, I have taken that using cyclic group properties, I have taken a subgroup generated by A, order is equal to P. I have taken another subgroup generated by P, B, order is Q. Step 3, simply I have calculated order of the element AB. It is equal to the order of the group. So whenever these two are equal, G possesses generator, it is cyclic. In a simple nutshell, I have used the three things there in proving the result. So in exam, by simply stating the three things, we can say that order of G whenever given as PQ, it is cyclic. So a group of order 15 is also cyclic. Not only 15, you can say 21 if you take, it is of the form 3 into 7, like that. But these conditions must satisfy. Whenever you have written two primes, P must be less than Q. P does not divide Q minus 1. This type of situation you should take care. That is most important. Let me say, if I have taken order of G is equal to 11 into 12. Let me say, I have taken order of G is equal to 11 into 12. So it is of the form P into Q. So P is less than Q and P does not divide Q minus 1, satisfies or not, most important. So if you take order of G is equal to 11 into 13, then this will be satisfied. Right? Therefore, whenever a group has order 11 into 13, it is cyclic as per this result. Okay? Are you getting the outline of the approach? So if you are interested, I will further consider the problems. Otherwise, I will close the session here. Based on your interest, I will continue. Fine. So I will take this problem. I think it is also given the previous year papers. It is a simple result. Take a note of this, then we will discuss. After noting, please tell. The number of silo P subgroups of SP, where P is prime number, is P minus 2 factorial. Here SP means the permutation group. So let me say, if you talk simply, say, I have taken S5. Here 5 is the prime number. So if you want to know how many 5 subgroups will exist for this group, it is nothing but P minus 2 factorial, nothing but 5 minus 2 factorial, nothing but 6. That was the objective of the problem. Okay? As per the question tag given, that was the result. Now see, whenever you consider 5 group, how many elements will be there in that group? The 5 subgroup, if I write 5. So silo P subgroup means it contains P elements. Let me say, if I have mentioned silo P subgroup. So what is the meaning of it? I have taken a subgroup whose order is P, and in that elements also possess order P. That was the idea. the underlined idea of that. Similarly, if I write 5 subgroup, means for this set I got a subgroup. It contains exactly 5 elements, and in that subgroup also element order is 5. That is the thing. Okay. Now for our generalization, here you will get 6 subgroups for this set S5. So what does it mean? Let me say I will take a cycle like this. F is equal to 1, 2, 3, 4, 5 in this S5. So what does it mean? F is nothing but this is the permutation I have written actually. Okay. Did you get it? How the permutation I have considered? Now see, since it contains a cycle of 5, for 1 it is 2, 2, 3, 3, 4, 4, 5, again 5 to 1. It is a cycle of order 5. So order of the permutation is 5. Let me say, we know that whenever order of A is n, you can find a subgroup. A power 1, A square, A cube, so on, A power n minus 1, because A power n is equal to identity. Or you can say A power n minus 1, an. This is a subgroup. Similarly, if you take F, what is the corresponding subgroup here? F power 1, F power 2, F power 3, F power 4, F power 5 is equal to identity. This is the subgroup. Please understand, each one contains a cycle of length 5. These are also nothing but cycle of length 5. So what is the idea here? Whenever you have taken a permutation of cycle P, then it will create a subgroup in which each element has order P. That was the idea I want to convey for you. Okay. Now, how many such cycles will exist? It is nothing but P minus 1 factorial. We can calculate that. How many such cycles will exist? It is nothing but P minus 1 factorial. That is always possible. So you randomly take an example. You take the simple thing A3. So I have taken 1, 2, 3, 1, 2, 3. So on 3 symbols, you write all the permutations. Now, cycle length 3 permutations you consider. How many such things will exist? You calculate. It is nothing but 3 minus 1 factorial, such permutations. Similarly, if you want to know how many such permutations will exist, as P minus 1 factorial. So, the number of cycles of length P is P minus 1 factorial. So, if you have a doubt, I will say like this. Let me say, in this set, I am writing cycles of length 5. This is one cycle. 1, 2, 3, 4, 5. You can take the other one. 2, 1, 3, 4, 5. You can take the other one. 2, 3, 4, 1, 5. You can take the other one. 2, 3, 5, 4, 1. You take the other one. 1, 3, 2, 4, 5. I think you can take one more. 2, 3, 1, 4, 5. This is a permutation of cycle 5. Its multiples, if you consider it is a subgroup. Now you calculate how many values will be there of cycle length P. Here also you get a subgroup. Here also you get a subgroup. Here also you get a subgroup. So in each subgroup, how many permutations you will get of length P or length 5, that you need to calculate. That result is nothing but P minus 1 factorial. That means here I will say 5 minus 1 factorial, nothing but 4 factorial, nothing but 24. Now you have a question. How it is true? Because if you say that it is a subgroup, every subgroup contains identity and other elements. Accepted? So identity has order 1. So see, this is a 5 cycle. This subgroup contains 5 permutations. Excluding identity, you will get 4. So this subgroup contains 4 permutations. Each will have order 5. Here you got 4, here you got 4, here you got 4. Total 6 fours, 24 permutations. Nothing but p minus 1 factorial, 24. Okay. That is the idea behind that. You got it? Now I will write the final step. Exactly. See, this is a 5 group. What is meant by 5 group? If you write multiples of this permutation, it contains exactly 5 elements in which one is identity. And each permutation has order 5. That is the meaning there. Right. So excluding identity, you will get the remaining elements. So here I am saying that consolidating the thing here, if you want to say P cycle of length P, how many will exist? It is nothing but P minus 1 factorial. So how many subgroups will exist? P minus 1 factorial by P minus 1. Nothing but P minus 2 factorial. That was the answer. Why I am dividing with P minus 1? If you know all total cycles, if you divide with the possible number, here you will get 4, 4, 4 like that, then you will get the remaining number of subgroups. See, here it contains 4 cycles, right? Let me say, the total number of cycles here are nothing but 24. If I divide 24 with 4, you will get 6. I have mentioned 6 subgroups, please understand. 1, 2, 3, 4, 5, 6. These are the 6 subgroups. So if you divide the total number of cycles with the number of values existed in each subgroup, you will get the number of subgroups. That was the idea in dividing that. P minus 1 factorial divided by P minus 1, that will give the number of subgroups we will get. That's it. Right. So this is the conclusion we can take here.